Hello everyone, this is Ayush. I'm a PhD student at Johns Hopkins University, and in this video I'm going to be presenting our work on occluded gait recognition titled Mind the Gap, Bridging Occlusion and Gait Recognition via Residual Gap Correction. So let's get started. So first of all, why is occlusion or even a problem in gait recognition? So I think it's from these examples it's easy to see. Um, Occlusion can arise pretty naturally in all of these scenarios. Maybe the camera is at an angle which does not capture the subject completely, or maybe there are some stationary objects like these traffic cones or these pillars which obstruct the subject from view even temporarily, or maybe there are multiple people walking in a group and they actually occluding each other from the camera view. So we try the existing state-of-the-art gait recognition models. We directly applied them on occluded data, and we observed that they don't perform very well. Right. So we need some methods which explicitly target this occlusion problem. Now there have been some methods proposed previously, but they have some limitations as well. Most of these works they use pretty small data sets, like a couple hundred videos, because first of all, collecting data is difficult, and then collecting data while occluding the subjects and having a natural occlusion, that is even more difficult. And some previous works which target the occluded gait recognition problem, they actually need paired holistic and occluded data. So you need an occluded sequence of the subject, and then you need the same sequence without the occlusions. This additional requirement makes collection even more difficult on more than it actually is. These are some limitations in current works, and then there is also one problem which we actually identify on our own, something which we call holistic performance retention. And what it is actually like existing works, they perform well exclusively on occluded data. So in this illustration, we see that previous works they form a cluster of embeddings of the holistic data of the same subject, and they form a different cluster actually of the occluded sequences. So within occluded sequences, like if both the probe and gallery, they are both occluded, they will perform well. But they actually, because they are trained on occluded data. But if the probe is holistic and the gallery is occluded, or vice versa, they are actually these embeddings are pretty far apart. So in the process of being trained on occlusions, they actually lose performance on the holistic full body data, or in the case where one probe is occluded or gallery is not occluded. So we actually inspire our solution from observing this problem, and we propose a kind of residual correction network, a separate network, to take the occluded features and map them to the same space as the holistic features, so that occluded and holistic data, they are both in the same cluster, and performance on holistic data is also retained. Right. Before we go into the description of our own method, there are some prerequisites which I'll just go over in 1 minute. But this work called Occlusion Aware Network, that's actually also targeting the occluded gait recognition problem, and that was proposed in VACV 2024. But the main idea behind this work is you can actually train a separate network which they call occlusion detector, which is different from the gait recognition network. So the occlusion detector is just trained to identify the different types of occlusions, or if occlusions are even present at all in the data. You train it on a simple classification task like this, and in the process the occlusion detector, it actually learns occlusion relevant features which help it in classifying the occlusions. But then you can use the intermediate features of the occlusion detector and insert these occlusion features, beta they say, into the gait recognition backbone, and that actually helps make the gait recognition backbone occlusion aware. Now I discussed this because we actually build on top of this idea. And now let me go to the description of our main method. So the overall idea of our method is based on this observation that current gait recognition networks, they work well with holistic data. If they are not trained on occlusions, like they work with holistic data, but their performance does not directly translate to occlusions, so they fail on occluded data. Now, if occlusions are present, now can we correct the corrupted features of these networks? Like, we want to try that. And for correction, like we introduce an additional network called the feature restoration network, or FRN, on top of a state-of-the-art gait recognition network, which we call gait signature extractor. So the GSE is actually it can be any publicly available model, which given an occluded sequence will most likely output corrupted features. And then the FRN is aimed to restore these features or correct these features. So FRN is a corrective network. Now, as we see in most current occluded gait recognition works, when you try to correct for occlusions, you actually disturb the performance on holistic data. So that's the same problem. Like if this correction overfits to occlusions, then we will not be able to perform well on holistic data. Now, the solution to that is that we can apply the correction selectively. We can apply the correction only if occlusions are present, right? And we do that by using an external network to regulate the correction. And we call that external network occlusion evaluation model. And then we have all these multiple modules. In the end, we fuse all the features of all these components, and I'll describe how we do that. But in the end, we obtain a single feature F, which is occlusion robust, as well as it retains holistic performance. And let me dive into the components in detail. So first, let's go over the occlusion evaluation module, and I've circled it here in this diagram. But it basically is the occlusion detector, which was proposed in previous work, the occlusion aware work, which I described. It takes a sequence, potentially occluded sequence, and it outputs two features. It outputs like a scalar alpha, which is kind of like a quality measure of the input, and like it is just a scalar. So we hope that alpha is higher when the occlusion is higher, and alpha is lower when the occlusion is less severe. So this is a quality measure, and the occlusion feature O is just the intermediate features of the occlusion evaluation module, or occlusion detector, which we discussed earlier. So that has information of like what kind of occlusion is present, where it is, and if occlusion is present at all. So the occlusion evaluation module outputs these two types of information. And then I already described the gait signature extractor and the feature restoration network. But to recap, gait signature extractor is a standard gait recognition network, which can take like any sequence, occluded or otherwise, and output a gait signature G, which in the case of occlusions is probably corrupted. And then the feature restoration network is actually like, it also takes the same occluded sequence, or like potentially occluded sequences as input, and it outputs a corrective feature R. Now, this output R is not just conditioned on the silhouette or like input silhouette sequences, it is also conditioned on the occlusion feature. So if you recall, like the occlusion aware work, the previous work which I described, that use the occlusion feature to guide the gait recognition network to make it occlusion aware. So we do the same thing here. The feature restoration network is actually occlusion aware, and it knows where occlusions are present, what kind of occlusions are present, and we hope that would help it to give a better corrective feature for the GSE. But yeah, so these are the two components. And then we have like three things which we have to fuse: the scalar alpha, the corrective feature R, and the gait signature G. And we do adaptive feature integration, but it's just another way of saying residual addition. So the feature integration module, which I've circled here, that actually takes the corrective feature R, it scales it by the scalar alpha, and then it adds it in a residual manner to the original gate signature G. Um, so and like that's how we get the final feature. Uh, so the final feature F is an occlusion enhanced gate feature, which is also like which also ensures performance retention. And the reason why is because the way we integrate it, we scale the residual feature or the corrective feature R by alpha. And if you recall, alpha is a measure of the occlusion present in the input. Now, if the occlusion is very severe, alpha will be higher. And so we'll be able to apply a higher correction to the corrupted gate features, and that's why we'll get a higher performance. But when the occlusions is less severe or occlusions are not present at all, alpha would actually be lower. And in this case, the gate signature extractor, which already knows how to perform well on holistic data, the G features will be ideal. So we don't want to disturb the G features. So that is achieved by having a low alpha during holistic, like when the data is holistic, and the corrective feature is like very close to zero, it's very small. So F is almost equal to G, and that's how we are able to maintain holistic performance. And the way we train, like just a side note, like how we train, we actually use a multi-stage training to ensure all of these subcomponents perform their desired task. In each of the three, like we perform 3-stage training, and each of these stages only one component is trained. So stage 1 is just training the OEM, which, as we saw in the previous work as well, like it's a separate training stage which just classifies, or which just trains the network to classify the position or the amount of occlusion. It's a separate training stage, no gate recognition network here. Stage 2 is just the standard training of a gate recognition network on full data. So here I've shown that stage 2 also needs full data, and like no other networks are used, just the GSE is trained. And in the third stage, actually, we combine all of these components, and then we freeze the OEM and the GSE, and we just train the feature restoration network. So we train FRN to output corrective features which can be merged with the GSE. Right, that's how we train the different modules of a network. And like these are the results we achieve. I know like these are a lot of numbers, but basically the main trend is our method is able to perform better than the other baselines on occlusions. At the same time, it retains performance on the holistic data. The upper bounds are shown in purple here as purple lines, and then we are able to like achieve performance very close to these upper bounds, but the other methods, they fall short. And of course, like our method is also model agnostic. Like we experiment with a couple different backbones for the feature restoration network and the gate signature extractor, but the idea is similar. Like you have a traditional backbone, a traditional gate recognition backbone, and then you have the same network copied as a correction network. Like the idea is same. It's model agnostic. We also do the generalizability and adaptability tests, which are also standard in occluded gate recognition these days. But we train on one set of occlusions, and then we evaluate in a zero-shot manner, or maybe with additional fine-tuning on different kinds of occlusions. And we observe that our method is more generalizable and adaptable to like unseen occlusion types. So yeah, thank you for the presentation, listening to the presentation, and more details are included in the paper. We also have a project web page which you can scan from this QR code. It has this website has a description of my other projects as well. And yeah, thank you. Please reach out if you have any questions.